thank you for everyone for coming to our talk today. We're really excited to have Dr. Eric Klaber from the Department of Statistics at North Carolina State University with us today. He's been visiting for 2 days as part of an ongoing grant project, and we've been working on some data analysis, but we're really excited to get a broader perspective today on what he's been working on. He's currently an associate professor in the Department of Statistics, and he's published approximately 40 peer-reviewed articles. And some of the more interesting things I thought I'd share, one of the students in his Stat 745 class said on a scale from 1 to awesome, he's super great. So I think you have a lot to look forward to today in terms of this talk. Other things that might be good for you to know is that he spent 12 years as a professional magician and performed more than 3,000 shows. He currently collects books on magic tricks and magic history, and once hung upside down from a crane and escaped from a straitjacket. So I think that probably sets the right tone for the title of this talk. So please help me welcome Dr. Klaber.
Thank you, everybody. This is going to be a lot less exciting than any of those things you just mentioned. But what I thought, I wasn't sure exactly what the mix of interest was going to be, and so I tried to do something where I would just give you a broad overview of the kind of things that I work on. And if any of those sound interesting, we can just kind of go off and talk about them. And also, we're always looking for collaboration, so maybe something will get your attention and we can talk about it afterwards. And then, because there was some danger that the biostats folks were going to show up, the second half of the talk, the second part of the talk is going to be a bit more technical and talk about one specific issue in personalized medicine, just one of the things that Janice and I are working on together. And so that's really, the title is really just about that part, interpretable treatment regimes by decision lists. So thanks Janice and Jordan for hosting me. I got to learn a little bit about soccer yesterday. That's good. And this is joint work at the NC State UNC Artificial Intelligence Precision Medicine Lab that I co-direct with Michael Pasrock, the Puerto Rico Department of Natural Resources, the Natural Science Foundation, NIH. And joint work with a lot of people. The person who did all the hard work for the second technical part is shown here. That's Ichi Zong. So all the hard stuff is his work. And I'll mention these others as we go through. So just a quick overview. I'll give just a broad coverage of the kind of things that we do in my group, and then I'll spend maybe 3 slides talking about one particular class of problems that I won't cover in detail today. I'll talk a little bit about our outreach, and then I'll get into this specific problem. Okay, so our group, which we humbly call Labor Labs, has 22.5 students and 8 labor robots. You can maybe identify the robots in that picture. And so 2 of them are UNC, so I have an appointment at UNC also in the biostat department. And then, so all the neat stuff is because of them. And I'll just try to take credit for it. So the idea of the lab is that we try to develop statistically rigorous methods, but that are also applicable, right? So we're trying to really be application driven, but we do a lot of methodological and theoretical work. And in particular, we focus on inference and data-driven decision making. And data-driven decision making encompasses almost all of statistics, computer science and data science, and all of these other quantitative fields. So in particular, we focus on precision medicine, so how to make better treatment decisions from data. And I'll talk about that in more detail, but our view is really to provide information to help people make better decisions, not dictate decisions. So there's a distinction there that I think hasn't really been made properly in the stats literature. Spatial temporal decision problems. So I'll talk about that for about 3 slides. And so these are a class of problems where we're working on things like urban planning, adaptive wildlife management, conservation, and also spread of infectious disease. And then something I won't really talk about, which is statistical inference for non-smooth functional. That's a technical topic that supports the work in the first 2 aims. And then K through undergrad STEM discipline outreach. And so I thought I would have lots to say potentially about that. So we're trying to bring statistics and data science to a larger audience. And then in terms of technical subtopics, we work on a lot of different areas, including causal inference, Markov decision processes, machine learning, statistical computing, dimension reduction, sequential games, and here games in the mathematical sense, where you have groups competing against each other, like there's a lot of security military applications, We work in human trafficking, drug trafficking, weapons trafficking, and so that's an example of a game, but obviously these are serious topics, right? We model mathematically these games. We also work on video games, which is a less serious type of game, and I'll show you a video of that in a minute. We work on disease modeling, both from an individual agent-based point of view and from an equation-based population level point of view, and then localizing topics, which is another technical. Okay, just to give you a sense for the kind of things, the kind of collaborations we have, we work a lot with industry, so I work with Ecolab on food safety monitoring with embedded sensing, Quintiles on clinical trial design, work with Cisco, data science, JMP with their interface to help people understand the content of statistical models. So one of the things that JMP really wants to do, if you haven't used it in statistical software, it's a sort of point and click. But if you fit a model, they want people to help understand the statistical uncertainty associated with that model and help them choose appropriate ways to quantify uncertainty. And then RTI, work with them on displaying real-time information about utilization of healthcare services, and then also sentiment about substance abuse. And then we work with a lot of different government agencies. One of these is Janus's. Okay, so the thing that I'm not going to get to in detail, but I think is a really open problem, and actually some of this is being done in Florida in terms of the Everglades management, and that's spatial temporal decision problems. So there's a huge potential to use data to inform these spatial temporal problems. So for example, adaptive conservation. So I'm going to stand up here. So on the lower left, this is Puerto Rico. Hopefully it was Puerto Rico. It's going to be gag where I get closer and it turns off. So this is Puerto Rico. This area here is the Bosque Modelo model forest. And so we are helping to choose tracts of land in Puerto Rico to bring the amount of conservation area from 8% to 15%. This is the largest conservation project ever in Puerto Rico. And in terms of percentage increase, it's the largest anywhere. And so the question is, how do we choose the right tracts of land? Both taking into account things like cost, but then also there's political constraints, and then there's a whole bunch of different species, so things that are good for birds may not be good for pollinators, and things that are good for birds and pollinators may not be good for frogs, and so on. And so how do we do that? How do we figure out what land is available and what we can do with it? And one of the big challenges with this kind of problem is communicating to those who manage the resources, right? So the Department of Interior actually has the money, right? They decide which tracts of land to convert. And so how do we communicate not only what we think the best course of action is, but the uncertainty associated with that, and then if they have to change something, it's a really tough problem if we say, okay, here's the map, these are the places you should convert. And they say, we can't do this one. Right? This is one track, we can't, for whatever reason, it's not available. It's intuitive to just take that off the table and say, okay, well, I'll do all the other ones, and I'll just pick a new spot. But it turns out, because everything is dependent spatially, once you remove one piece, everything else can change. Okay, so it could be that one piece connected two landscape corridors. By removing it, you totally change the way the animals are going to move about the island, right? And so helping them understand that if you give them a set of locations, they are all dependent on each other is a big challenge. Wildlife management, so this is a predatory seagull. You guys probably know about these, maybe you don't. I didn't know that seagulls could be predatory, but they eat things like skimmers and terns, and so the Department of Natural Resources wanted to go out on these islands and kill them. That means they shoot them. And so they wanted to know which islands they should do that and what the effect would be on other species. We work in urban planning, so that's obviously a big one in terms of doing traffic sensing and traffic rerouting in real time. Video game AI, I'll show an example of that in a second. And then the canonical example, the one everyone likes to think about, is infectious disease management. Okay, so let me just say a couple things about why that's maybe an interesting problem. So one of the big things that technological advancements has been monitoring and surveillance of infectious disease. That's increased a lot. Social media, people tweet about being infected with things and so on. And so there's this increased ability to monitor infectious disease, and you can get this just from government humanitarian agencies, but also social media, and then there's compulsory disease reporting. So what we're trying to do is we're trying to take big data plus domain knowledge plus big computing so we can decide where, when, what, whom, and so on to apply to intervention. And the idea there, of course, is to get better public health, but you get lower resource consumption, which is a big problem when you're talking about public health interventions. And then we also want to be able to generate new scientific knowledge, and so that fits into this interpretability piece, which I will get into in detail in a second. So to illustrate why this is a tough problem, I'll talk about one example, which is white nose syndrome. Have you heard of this? This is a disease that's killing millions of bats across the U.S. And so, well, I almost gave the citizen headlines. So, fungus is killing millions of bats and going away. I like this one because of the term baticlism. The secret baticlism, white nose syndrome and extinction. And so there's this fungus, and you can see it on, here's a bat hanging upside down, there's a little bit of white on its muzzle. So this has white nose syndrome. So this fungus gets in where they're hibernating, it just spreads across them because they don't clean themselves. And it kills them by the millions. So there are these caves we would go to visit, and we'd say how many bats are here, and they'd say, oh, there's 25 bats. So how many used to be here? And they'd say, I don't know, 150. And I'd say, oh, well, I mean, that's a pretty big reduction. No, 150,000. I mean, it just wipes them out completely. So the only ones that were there had come from somewhere else because it had just killed them all, right? So, and maybe you don't care about bats, but they eat a lot of insects. They have huge economic impact in terms of pest control. And then, of course, there's ecosystem stability and robustness, that kind of thing. So here's a potential intervention. This is a cave. It's an artificial cave. And it's an interesting bit of trivia. It's built from Corvette parts or byproducts. But these caves are about $1 million a piece. So they want to know where they should put them. Ideally, they just put them everywhere, but they can't afford to do that. So when they came to us, the first thing they said was, okay, so we have these. We need to know where we can put them. We can only afford a very small number. Okay, so what's the most effective place to put them? And so the problem is a statistical problem or is a decision problem. Looks like this. Here's the U.S., of course. And these outlying counties have caves or mine shafts that house hibernating bats. Okay? So these are the places you might want to put one of these artificial caves, for example, or do some other kind of intervention. And it's color-coded by the spread. So it starts up here in Schoharie County, and it spreads through the northeast, and then goes across the Midwest. There's even been some reported cases out here now. This data's a little old. And so an allocation strategy takes all the information you have, that would be where the disease is and where it's been. You have information about each one of these little counties, things like winter temperature, species richness, things about how many people live there, what percentage is urban or rural, that kind of thing. And you choose a subset, you treat the subset, you go out, you resurvey everything, you get updated information about the disease spread. And now you can change where the caves are, you can leave them where they are. Okay? And that just goes on forever until the disease is gone or the bats are gone. Okay? So, why is this a hard problem? It's a hard problem because at the beginning you have no data on intervention effectiveness. It turns out bats are really hard to keep in captivity. So they have almost no information about how well these work and how well they're going to control the spread of the disease. You have noisy, incomplete sparse measurements. So I described the problem very cleanly as that we know everything everywhere all the time, but somebody actually has to go out and take those measurements, right? So they're doing that partially by convenience. There's obviously measurement error. They go there, they think there's the disease, but it's really not there. Or they miss it when they go to a cave. High dimension also in white nose syndrome, there's about 11,000 measurements per time point. Okay, so we have 11,000 input variables at every time point. In terms of estimation and inference, this is an online problem. What that means is we have to estimate the disease dynamics as we go, because we don't know what they are. But then we also have to make decisions. So there's always a trade-off between making decisions that look best given the current model. And so you have a model, you say what would be the best thing to do with this model, we're right. Or taking actions that are going to give you the most information to improve your model. So this is a fundamental trade-off. And so from a statistical point of view, this means the sampling distributions are complicated. It's hard to do inference, it's hard to do prediction without adjustment. And then computationally, it's challenging because if you have L locations, so in white nose there's 1,100, there are 2 to the L possible allocations. So to give you a sense, this is many orders of magnitude more than there are atoms in the universe. So you couldn't enumerate your choices if you had a supercomputer and you had tens of thousands of years. Right? So you can't even enumerate what your possibilities are. So you need some way to cut that computation down. And we're not looking to make a decision at one time point, we're looking to make it infinitely far in the future. Right? We're trying to go forward in time. And so you have to come up with some way to cut down this computation. So there's a lot of challenges in terms of the actual computation and the theory, but there's also this communication part, because these policies aren't going to be used blindly by policymakers. There's big money at stake, there's politics, there's also logistical issues. And so what we really need is we need to run these models in the back end, which I'm not going to tell you about. I'll tell you about some other horrible models in a minute. But we need a way to communicate uncertainty, communicate recommendations, and then also be able to explain this is what we think is best. But then if you're not going to do that, what's next best, and so on, and find ways to let people interactively explore the models. So just to give you a sense for what's the status of that project, we have parametric and semi-parametric estimators. And they can scale up to about 100,000 locations. And so, white nose are locations, but in an infectious disease of people, these are people, right? So you have 100,000 people in a small city or a moderate-sized city. You can sort of run this. We have a number of different application areas. We're working with cholera in Zimbabwe, malaria. This just got funded in the Democratic Republic of Congo, looking at seasonal flu models, and of course white nose, and then we have some data on Ebola from the most recent outbreak. So there's a lot of different application areas. They all have their own issues with the data and so on. But there's a lot of problems that have the same features. So I talked about the disease issue, but adaptive conservation, I mentioned wildlife management, urban planning, video game AI. They all have the same mathematical structure. You observe the status of some system, you have a large set of actions you can take. You take the actions, you can see what happens, and that just goes on forever. Okay? And so they all have the same challenges. Okay, so one other thing I wanted to sort of just pitch, because I thought there might be some people here who are interested in this kind of thing, and we'd love to get your help, is we're involved in outreach, and particularly trying to get people excited about statistics and computer science. And I don't know if you've ever seen any statistics outreach, but it's often, it can be, I don't know, I'm trying to think of a politically okay way to say how boring it is. It's very boring. And so we're trying to change that, because I think, I'm going to do this for a living, so obviously I think it's interesting. And so our goal is to get high school and undergrad students, and some younger students also, interested in statistics through video games. And so there's a lot of educational games where you play a game and it tries to teach you about some topic. My daughter plays a lot of these learn your letters kind of games. She's 3. But what we do is we take real video games that are complex and difficult and hopefully fun to play, and we teach you how to teach a computer to play them. So the task is scraping the data out of the game and then learning to play optimally as a decision problem. And just like the white nose issue, what you have is you have the screen of the game, that's your state. You have the actions you can take, the controls you can move, and then you have your outcome, which is the score, and that goes on for as long as the game lasts. Okay, so it's the same problem, they just don't, it's just more exciting for them. So we do a few different things. We have a summer research program, which is a virtual summer camp. We do displays at different museums. We just did one at the Natural History Museum. We do a webinar series for high school students, that's through the American Statistical Association. And then we have two video series. One is 2-minute stats, so we try to explain a statistical concept in 2 minutes. And so we release those. And then we also have our web series that should come out this year. It's called Shapes and Capes. These are the characters here. And I thought I would just show the kind of thing that here's the kind of thing that we show to high school students to try to get them excited about video games. So I'll show you a game in a second. So this is one of the games, so it's called Laser Cats, and so this is a stripped down version, so the cat is trying to shoot the mice. So we let them play this. There's actually 9 levels, but this is just the first one. And so the computer is now, we show them, after they play, we show them how a computer can learn to play. So the computer knows only what it can do, which is up, down, left, right, northeast, southeast, and so on, and it knows its score. One thing it doesn't know, but you can learn from experience, is that the farther you are to the left, the more points you get. So killing a mouse is more valuable if you're farther to the left when it happens. And so after about 90 minutes, it can play as well as any human. And they think, okay, that's kind of neat that the computer learned from experience. But if you let it go for 7 hours, then what you see is the computer plays perfectly, right? It's very far to the left, it kills all the mice as soon as they come out, and this is clearly better than they can play, even the ones that are gamers, right? And then so hopefully we have their interest, and then we try to show them some more interesting bits about computer learning. So what we're going to do next is we're going to release an enemy it hasn't seen. So you can see how all these mice are the same type of enemy. So now we're just going to release a new enemy that the computer hasn't seen, and it adapts immediately. The very first time it comes out, it adapts to that new enemy. And so it has to shoot it more times, and so when it comes out, it'll slowly back up and keep shooting. Right? So you get this generalization. So it can generalize like a person can. There's something in the back end here called reward shaping. And then just to really drive home the point of all the power of data-driven decision-making and computing, we're going to now release mice at the same rate that the cat can actually shoot. And so you can see that obviously this is something a person can't do. It has to plan in real time, because it doesn't know where these mice are coming from. They come out randomly. Exactly what path it's going to take so that it gets every single one and it's as far to the left as possible. And so we show them this, and now the idea is, okay, we're going to have them actually go through and implement this. Okay? And we have all this layering on top so they don't actually write the code. So they can manipulate the pieces that drive the AI, and then so they go through the exercise of learning. So that's sort of our approach play the game, show you a demo of a computer playing the game, and then we actually have them go through and replicate the AI. And how much detail that involves depends on their level, obviously. So for early high school students, we give them slider bar kind of things that allow them to manipulate the different pieces of the AI. And then for older high school students and undergrads, we give them a little bit more freedom over the actual tuning of the algorithm. So that's something we're currently involved with. If you have better ideas for us to communicate some of these concepts, I would love to hear them, or if you want to partner up. And now the plan is to totally switch gears and talk about one very specific thing in precision medicine. Okay. So, what used to be called personalized medicine, it's now called precision medicine, but the thing that people like to say is you want to get the right treatment for the right patient at the right time. So this is sort of the mantra of personalized medicine advocates. And when I say personalized medicine, this is something that's been in practice in medicine for more than a century, right? This is what all clinicians are trying to do, right? They're trying to use your individual characteristics to dictate your treatment. So what I really mean is data-driven personalized medicine, which is now often called precision medicine. So it's obviously widely recognized the best care is going to require treatment decisions that are tailored to individual patient characteristics, including preference and family history and so on. And if you do this correctly, you can get better outcomes, but you can also reduce cost and patient burden. You can reduce over-treatment burden, this kind of thing. And so a treatment regime is one way to formalize or mathematize clinical decision-making, and you do this as a sequence of decision rules. So it's one per stage of clinical intervention, and these stages of intervention don't have to be fixed in calendar time. They can be driven by patient outcomes, right? So your condition worsens, so we have to change your treatment, for example, or you're doing better, that kind of thing. And so they map current patient information to a recommended treatment. And then we'll define an optimal regime as maximizing the mean of some cumulative clinical outcome if applied to the population of interest. So you have some utility that measures how well you're doing. It could be a quality of life score, or it could be some measure of efficacy or side effects or something like that. But we've agreed upon what good means, and we're going to try to maximize the mean of that outcome if we were to take whatever our rules are and apply them to the population. That's the idea. So what does one of these look like? Here's an example. This is mobile health intervention for post-traumatic stress disorder in cancer patients. And this is with Sophia Smith, who's at Duke. So there's two stages. In the first stage, we read out the rule as if distress is greater than 3, if your distress score is greater than 3, then you get something called the cancer distress coach. So it's if you satisfy this condition, we recommend this particular treatment. Yeah. Otherwise, so if your distress score is less than 3, but your PTSD symptom score is greater than 20, then you still get this cancer distress coach. Otherwise, you get standard care. Okay, so this first rule says if you're severe on either one of these scales, distress or your PTSD symptom score, then you get usual care. Or sorry, then you get CDC, otherwise you get usual care. And then among patients that are in this first stage that don't respond, they're then subjected to they then get a second decision rule. So if they're a responder, then they just get the first stage treatment. So if they're a responder, they don't get any change. Otherwise, if you're using CDC and your PTSD symptom score changes by more than 3, then we add mobile coaching. Okay, so this is another mobile intervention. Otherwise, if you're using CDC and your distress score is now more than 4, we're going to add FaceTime cognitive behavioral therapy. Otherwise, you get FaceTime CBT only. Okay. So the point here is you can see that it's dictating someone's treatment based on their individual characteristics and also including how they responded to their first stage treatment. And this is just a simple 2-stage rule, but you could have an arbitrary number of stages. Okay. Make sense? So the goal is to use data to estimate one of these rules so as to maximize an outcome. So in statistics, there's a lot of work in this area now. It's a very hot topic. And the way that statistics talk would normally go here is they would say, here's an example of a treatment regime. Right, we want to estimate the best one, and now here's the way in which we would do that. And a natural thing to do is to say, well, we're going to assume that the regime that we estimate, the set of rules we estimate from data, is going to be used to dictate treatment choice for patients. Right? So we're going to take the rule we estimate, like the one I just showed you, and we're going to apply it to patients. And if you do that, you worry a lot about flexibility. You want to fit the best model possible. Right? That should be your focus. You want to make good treatment decisions. But the reality, well, let me say one more thing about it, just to complete that thought, which is that if you take this view, then you really focus on things like machine learning and parametric methods. You want as much flexibility as possible. Yeah?
So in your previous slide, how do you measure stress? What type of sensors do you use?
Oh, okay. So these I think both of these are based on an itemized questionnaire that you give them. Yeah, so you're asking them about how they, about their symptoms. Yeah, good, thanks. Yeah, they're not wearing a sensor or something, although that would be really interesting. There's a lot of work on that now, right? Yeah. Good, thanks. So, just focus on machine learning. There's a bunch of different things that have happened recently. Direct search with large margin classifiers, generalized additive models, nearest neighbor methods. So these are all very flexible models. And in fact, in the Joint Statistical Meeting, which is the big stats meeting every year, both the Journal of the American Statistical Association, which is the flagship journal, they present 2 papers every year that are the highlight papers of this conference. It's a very big deal to have one of these. And both, they have 2 of them, the theory, methods, and application case studies, both of them were on flexible estimation of dynamic treatment regimes. They were both on non-parametric estimation, so the statistics community is really putting a lot of effort and resources into doing this, into doing machine learning for precision medicine. But the problem is that the reality, most of the time these regimes are estimated as part of a secondary exploratory analysis. Okay? So you design your trial, for example, and your trial is going to have some primary outcome that's going to be simple. Compare treatment A with treatment B, right? And then, so it's sized for that, and then you do all this additional modeling of the data that you didn't size for, that you're not controlling error rates for, and then you try to generate new hypotheses to follow up, right? That's what these regimes are used for. So the one I showed you says something about whether or not the cancer distress coach is really only valuable for people who are with more severe symptomology, right? But it's not, there's no type 1 error associated with that rule, because the study wasn't powered for that. And so if you take this point of view that you're just trying to generate new hypotheses that you can pursue in a secondary study, which is almost every sequential multiple assignment randomized trials, the kind of trials you use to estimate one of these treatment regimes, then you should really emphasize interpretability in a domain context. You want to generate information. Okay? Because these black box methods are never going to be used. If you take a black box treatment recommender and you just expect somebody to start making treatment recommendations, writing prescriptions based on one data set with some mysterious statistical technique that you applied to this one data set, which wasn't powered to do this in the first place, I think that's not a realistic expectation. So here's a very simple schematic kind of for how these things go, at least in our experience. You have some clinical hypothesis, you design your study, collect your data, but then when we do our primary analysis here, then we estimate a regime as a secondary analysis. And then we look at that and we say, does that make sense? Does that match clinical theory, right? Is there anything interesting there that we might follow up? And then you get new hypotheses and it sort of goes around, right? This is an iterative, collaborative process. Okay? And so our point of view now is to look at estimating treatment regimes with this model in mind, right? Generating information, generating hypotheses, and to facilitate this long-term iterative process. Questions on any of this? Please stop me. Okay, so one way to get interpretability is to use lists. So the example I showed you is an example of a list-based regime. So our goal is to estimate an interpretable but still flexible regime. And list-based rules are if-then rules. So if some condition, then give this treatment. Else if this condition, then give this treatment. You go all the way down. And then there's some terminal treatment recommendation. So for example, if your distress is greater than 3, then give CDC. So here your clause is your distress greater than or equal to 3, and here's a treatment recommendation. And then else if your PTSD symptom score is greater than or equal to 20, then give it CDC, otherwise give usual care. Okay, so that's the idea. And the nice thing is hopefully these are interpretable in a domain context. It doesn't need any statistical explanation. You can just read this off and say, does it make sense or not that we should give CDC to these 2 groups and usual care otherwise, right? And so you can focus on the science and not focus on statistics. And I just want to mention that some of you who have worked on this may have seen linear models as being recommended as an example of an interpretable model. Okay, where it'll say, if beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 is greater than 7, give treatment A, otherwise give treatment B. But actually that's very hard to interpret, right? That delineation is a hyperplane in 4-dimensional space, right? So it's not really something that we intuit, right? So we kind of try to put examples in and see who's getting what, but it's actually not very clear, whereas we hope at least that this kind of rule is something that allows you to focus on who's getting what, and then you can ask why they're getting getting those treatments. So these list-based regimes, they have a lot of structure, but they still can express a lot of different kinds of rules. So you can do things like give treatment A if and only if all of these hold. You can express that as a list. Give treatment A if any of these hold. And you can give a different treatment for every level of a categorical variable. Right? So there's a lot of flexibility, even though they're very structured. And we're going to restrict attention to clauses that are dictated by the union or intersection of thresholded regions, so like xj greater than some cutoff tau j, or xj less than or equal to tau j, or xk greater than tau k. The idea is that, well, mathematically you could let these be arbitrarily complicated clauses. It sort of destroys the interpretability if you let them be complicated. And this sort of thresholding tends to help facilitate interpretability. Is your risk score high or not, right? Do you have a college education or above or not, that kind of thing. Okay, so an interesting thing about lists is that they don't have to be unique. So here's two different lists, pi and pi prime. And so pi says if C1 then A1, else if C2 then A2, else A3. Here's the exact same regime written another way. If not, so this is a negation, if not C1 and not C2 then A3, if not C1 then A2, else A1. So these are analytically equivalent. They are the same rule. Okay? And so, from a mathematical point of view, this may not be desirable. But from a practical point of view, it's very useful because suppose that to evaluate C1, that might be something like how big is the tumor, right? How much volume is in your tumor, right? And this might be, are you male or female, okay? So these have two very different costs. And I mean, obviously, I think that's probably unrealistic. You would just do sex or tumor size, but maybe it's a blood test. But they have very different costs to the person, right? They have very different risks. And so the idea is that you can order these in a way that the risky stuff is at the bottom, right? The cheap stuff's at the top. Okay, so if you're just doing a blood test, that goes at the top. And then you only measure, say, the volume of somebody's tumor, or you only go in and do a biopsy if you have to. So you reorder them. So if somebody evaluates C1 to be true, you don't have to measure C2, right? So you can short circuit the rule. So the idea is that we can build these lists in a way that minimize patient burden or minimize time. And this idea comes out of, I did a consulting project for a call center. Sorry, don't judge me. But one of the big things is getting people off the line, right? So you want to ask questions in a way that allows you to hang up if you can, right? So obviously you want to ask the obvious, easy to get to questions first, and then you go down and progressively get more complicated. And so the same thing happens here. We do the easy measurements and the more complex measurements. So I'm going to focus on estimating just a single member of the equivalence class of these, but we have an algorithm that can give you the best one within the class for any measure of patient cost or burden. Okay, so we have an efficient way of doing that, and I can send you the paper if you want to see it. Okay, so we're going to do a little bit, this is going to be a little bit technical in the next few slides. I'll try to give the big idea, but so we're going to try to formalize the decision problem as follows. So what we get observed for each patient, we observe x1, a1, x2, x2, a2, x3, a3, and so on, all the way up to xt, at, and then some final outcome y. So here, xt is the measurement you get on a patient during period t. Okay? So in our two treatment stage, you get x1 before they get their first treatment, you get x2 during their first treatment, and then you measure their final outcome after the second treatment. A is the treatment, okay, so we'll assume it takes values in some sets, we'll assume it's finite, so you can just think about two treatments, for example, but it could be more complex than that. Then y is the outcome, it's just a scalar, so just a single number, and it's coded so that higher values are better. And then to summarize what information the decision maker has at the time the decision is made, we'll define a history. So h1 is x, obviously x1, that's all the information you had to make a decision at time 1. And at time t, you have all the information you had before, ht minus 1, and also the treatment you gave during the last period and the covariance you measured. So that's what you have available to make a decision. You have to base your decisions on that. Then formally, a treatment regime is a set of rules, pi 1 through pi t, where pi t takes as input a history, h, and it gives as output a recommended regime. So a patient who presents with history ht, little ht, is assigned treatment pi t of ht. So it's just a sequence of maps, one for each decision point. What goes in is all the information you have at that time. What comes out is a recommended treatment. And our goal is to maximize the outcome. So the way that we formalize this, and so the math here is kind of horrendous, but I'm just going to give you the idea. So the way that we conceptualize all this stuff, and one of the reasons we do this so meticulously is because this also applies to observational data. We want to be able to do this with things that are not in randomized trials. Okay, so we have to be very careful about formalizing what we can and can't say from the data. So what we can do is we can define what are called potential outcomes. So A bar T, this is a sequence of treatments of length T. Okay, so it's just some sequence of treatments. And then we can define all the things we would see if you were to get that sequence. So H1 is your initial history, there's no treatment there, that's just what you have and presented. But then we could say, what would your history be if we gave you A1? And what would your history be if we could have an H2 or an H3 star of A bar 2, all the way up to H star T of A bar T minus 1. This is what's the whole history we would see if you got this treatment sequence. And then finally, what's the outcome we would see if we give you this treatment sequence? So we can ask of each of you, what would happen if we gave you a different treatment sequence, right? And then you can formalize what would be the potential outcome, this final outcome we would see if we gave you treatments according to regime pi. So we'll call that y star pi. And it's formalized with this expression here, but all that's happening is it's just picking off the treatment sequence you would get under pi. That's what's happening. So the left is just the outcome you would get if we were assigning treatments with pi, and the right is a way to mathematize all of that, which I think I'll just gloss over. So the optimal regime in some class capital pi of potential rules you might use, in our case will be lists, satisfies this. The expected value of the outcome you would experience if we use this rule is at least as big as what you would get under any other rule. So if we use our list-based rules to make treatment recommendations for you, it'll lead to the best outcome on average. Okay. Now you might say, well, what about something else, like a median or probability, and we can do it. That can all be done, but this is the simplest, I think. Okay, so what are the assumptions we need? So formally, we need the following assumptions. Sequential ignorability that says that treatment assignment is independent of the potential outcomes given the history. What that means is that the treatment recommendation is based on things we've measured. So we're not doing things like recommending treatment 1 to people who are sicker than people who get treatment 0, and not measuring how healthy you are, right? So all the factors that are important for choosing treatment are being captured in this history. We're measuring them. There's no unmeasured confounders. So you may have heard of no unmeasured confounders as an assumption. If not, this is just a more general definition than that. But the basic idea is that you're not assigning treatments in a way that is going to systematically bias your results because you didn't capture what you were using to make treatment assignments. There's something called positivity. So the idea is that the treatments are assigned in such a way that they have a positive probability of being assigned for any treatment you might be interested in. So obviously if we give treatment 1 only to one group and treatment 0 to another group and they're completely disjoint, we can't estimate what would have happened if we had done the opposite, right? Because there's no crossover. And then consistency, so that just says the outcome, the history we actually observe is this thing we call the potential history under the treatment sequence you actually gave. And this is sort of like a tautology, but yeah, we won't get into that. And whether or not this should be an assumption or something that's true from nature. But, and then we'll also assume that we have what's called a stable unit treatment value assumption, which just means that the treatment you get doesn't affect the outcome I experience. Which isn't always true if we were in, say, group therapy, right? Or if we're friends and your treatment's really working for you, maybe you talk to me about it and that convinces me that I should really invest, and then I do better, right? So it doesn't always hold, but we're going to assume that the assignment you give to one person doesn't affect the outcome of another. And you can show that these are satisfied by construction in a sequential multiple assignment randomized trial, or SMART. But in an observational study, you have to think carefully about whether or not these are realistic. Okay, so I promise not too much more notation. So here's the idea. How do you estimate these optimal regimes from data? And even though this is complicated, it turns out all this is, those are SAS users, it's just a regression step and a data step and a regression step and a data step. You just alternate those. That's it. So it's actually, you don't need specialized software to do this. It's very simple. It's just that sort of getting all the formalized math makes it a little bit ugly to look at. But so let IT denote the space of list-based rules, okay? And we'll assume that those causal conditions hold. Then if I define QT, HT, AT, so this is a function of the history at time, the last time point, and the treatment at the last time point, the expected outcome given that history and treatment. So this just measures what do we expect to see for you if you have this history and we give you this treatment. So if you knew what that was and you're at the last time point, the natural thing to do is give somebody the treatment that makes that as big as possible. Right? And it turns out that that's true. The optimal regime is the treatment that maximizes this. So formally pi t opt is the argmax over pi t, the expectation of qt ht pi of ht. But all this says is, if you knew what this was, the best treatment to give somebody is one that makes this as big as possible. Okay? And then Bellman showed that we can use dynamic programming to do this for all times t. So you define qt ht at. This is going to measure how good it is to give you treatment at in history h, given that you have history ht, and you act optimally in the future. So if you make the best decisions as possible in the future, and you have history ht and we give you at, what's your expected final outcome? So that's formalized as follows: expectation of the next q function, given the next history. You're going to follow the optimal rule at that time, given your current history and treatment. And then you can show the best thing to do is to give the treatment that makes this as big as possible. So the bigger picture message here is that this is an expectation of y given some covariates. So you can estimate that with a regression, right? You can just fit that into procreg, or you can use LM and R, something like that. And then you just have to maximize it. And then recursively, this is it's a horrible looking expression, but it's something you could compute or approximate from the data, given covariates in treatment, which we can treat as a covariate. So again, it's another regression. So what you do is you do a regression for this, maximize, fit another regression, maximize, and this just keeps iterating. Okay? So you can estimate these optimal rules with data without having to do anything beyond regression, basically. Okay? So that's the idea. Okay, so I'm going to skip over and get to say something about computation. So you might be thinking that if you wanted to build one of these lists, you start thinking about, well, what are all the clauses I could use? And then you start thinking about, well, I have a first clause, but then I have a second clause. Maybe you think what the second clause is first before I do the first one, and then you think about the third one before I figure out the second one, right? And it becomes this combinatorial explosion of possibility, right? But it turns out that what you can do is you can use a stepwise splitting procedure. That's in the spirit of classification and regression trees, if you know what those are. And what's surprising is that you can show that you only need to consider the first split first, the second split second, third split third, and so on. And you can still get a global optimum, which is not true in classification and regression trees, okay? But it is true in this case. And so the way that this works is you optimize some measure of how well you're going to do at the end, plus a complexity penalty. And we have a stopping criteria based on the significance test. So you can show you get the global optimum. And you can also show the time at which it takes to fit the model as this form. And I'll just point out that there's an n and a log n here, and then there's some constants. And so n log n is not very expensive. Okay, so doing a matrix factorization is order n cubed, which is much bigger. Okay, so you can fit this to huge data sets. You can use this with massive observational data very quickly. Okay, so that's sort of the take-home message. Okay, so just some assurance that it works. If you make these causal conditions, you can show that the estimator, the probability it doesn't equal the optimum, converges to zero in probability. So that means you actually get the right answer as you get enough data, which is reassuring. And you can also show that under these conditions, if you look at the best outcome you can get, so this expectation of that potential outcome under the best policy, if you subtract off the potential outcome under the estimated policy, this will converge to zero as the data accumulate. Okay, so the outcomes your patients will experience will be as good as if you knew what the optimum was in the first place. Okay, so thanks for bearing with the symbols. I had to prove to the biostats folks that I knew what they were, but then they didn't show up. So okay. So here's the basic idea is that we have this flexible regression framework, but we can still estimate list-based rules. Okay, so we can still make them look like lists. And they give you they're interpretable, but they're expressive. You can get a lot of flexibility out of them. And it turns out you can do diagnostics. So you might say, well, fit the list. How do I know if the list works, right? What if I'm giving up a lot by using a list? Maybe I should have used something more flexible. You actually can do diagnostics. So it turns out you can compare the general maximizer of this Q function with the maximizer of the list-based rules, and you can compare how well they perform. So you can do this direct comparison. You can short circuit to save cost and burden. Some potential drawbacks, so you do get, I didn't show you the convergence rates, but they are subparametric, so that's a potential problem. We're still working on methods for inference and uncertainty quantification, and so getting things at confidence intervals is still an open problem. Okay, so I wanted to just illustrate with some simulated experiments So what I'm going to do is I'm going to take settings from two very well-known papers, Zhao et al. And Murphy. This is sort of the seminal paper in this area. This is sort of a very highly cited paper about machine learning in this context. And so the point of both of these papers was to illustrate why you need flexibility. So particularly this one is called New Statistical Learning Methods for Dynamic Treatment Regimes, so why you should be using machine learning. And so our hope was, when we set up to do this set of simulations, was we take these very flexible models, and we show you, generative models, and we show you wouldn't lose too much. So the idea was, you're going to use the lists, and the lists are way more interpretable than the black box you get out of the other methods, but maybe they'll perform a little bit worse, but the interpretability will be worth it. That was sort of the goal. And surprisingly, actually, the performance is pretty good. And we don't seem to be losing very much, and I'll say more about that in a minute. But the basic framework, I won't give you the generative models, but the normal covariates, they have some kind of autoregressive structure. Treatment assignment mimics both a randomized study and an observational study, so we have both cases. Okay? The mean outcome is nonlinear in the history, so it's a highly nonlinear problem. And so there's 4 models. They have anywhere between 2 and 10 stages of treatment, anywhere between 3 and 50 covariates, and then the propensity score, I use that just to remind us whether or not it's constant, which would be a randomized trial, or it depends on the patient covariates, in which case that'd be like an observational study. And so there are 2 constant and 2 history dependent. So the idea is we're going to try to cover these different scenarios. And as a performance measure, we're going to look at the expected average performance. So this is how well you do on average if you use the estimated rule. And there's 2 expectations here because this one is over the distribution of y star and pi hat, and then this one's over all the pi hats. We'll look at Q-learning plus policy search with decision lists. That's what we propose. We'll look at using a machine learning technique for Q-learning, which is just estimating those Q functions directly and maximizing them with something called random forests. We'll look at linear Q-learning, so you linear models, but you have a lasso penalty. And then we'll use something called backwards outcome-weighted learning, which they call BOLE. But as an aside, this group has 4 other methods. There's simultaneous outcome-weighted learning, which they call SOWL. There's doubly robust outcome-weighted learning, which they call DOWL. There's iterative outcome-weighted learning, which they call IWL. So if we were going to keep that trend going, we wouldn't call this BOLE. But anyway, so okay, so we're going to look at 1,000 Monte Carlo replications. So we'll do each of these experiments 1,000 times. Perform the estimated test. We'll estimate the performance with a test set of size 10,000. Look at training sets of size 100 and 400, and the maximum list depth is going to be set to 5. So we don't have lists that are longer than 5 clauses because they get hard to interpret. Okay, so here are the results. So they're grouped by row. So these 2 rows are model 1 with n equals sample size 100, 400. This is model 2 with 100, 400, and so on. So if you look at the performance, this is higher is better, and it's bolded if it's best. I didn't show the standard errors, but they're in the second digit. Okay, so decision lists, surprisingly, were very competitive. In fact, they were the best performing model across all but 3. And if you look at the ones where they were suboptimal, this is 6.63 versus 6.7, 6.66 versus 3.66, 3.68, and so on. And so actually they were very competitive in terms of performance, which was a surprise. We were hoping that we just wouldn't lose too much. And part of that is because they induce a lot of parsimony. So in very big, noisy systems, you get automatic variable selection, which tends to reduce variability. You might be wondering why there's NAs here. It turns out that the BOLE method can't scale to problems with more than a few decision points. This is 1 of 10, so it can't fit that. You can see there's a big difference between decision lists and lasso and random forest in some of these models, and it's striking how big of a gap there is for some of these. In particular, if you look at lasso, it's very drastic. And so that was sort of a nice, unexpected finding. So just to summarize, if you use Q-learning plus policy search with decision lists, this tends to perform favorably to both parametric and non-parametric models and machine learning kind of models. And part that may be because the parsimony of the list gives you some kind of automated variable selection. We didn't consider the setting with dense but weak signals, which is arguably not going to be improved by doing variable selection if they're very diffuse. And so that may be a place where this is going to perform worse. It's significantly more interpretable than the alternatives. And if you want to use it, there's a package called Decision List, which I can email you. It should be on the comprehensive R network soon. We're just waiting for our papers under revision. So in the interest of anonymity, which I just destroyed, we're not supposed to post it up there yet. So just some final discussions. Estimation of optimal treatment regime is often a secondary in the hypothesis generating analysis. It's not usually a primary analysis. We have one paper on how to size a study for estimation of optimal regime, and it's very complicated. And that's just for one stage, and for multiple stages it becomes even worse. But if we use computing with policy search with decision lists, then we can get these interpretable regimes. It's computationally efficient. You can show it's consistent under weak conditions. And because of these underlying regression framework I mentioned, where you do a regression, then a maximization, then a regression, you can use this with any kind of data. You can use it with ordinal data, you can use it with survival data, you can use it with high-dimensional data. Anywhere you can fit a regression model, of course, that applies to almost anything. You can do this. You can use it with continuous treatment. So if you had dose, for example, that you were manipulating. You can also do it for infinite decision problems, so those that go on forever. So if you're doing mobile health, where you're just going to keep giving interventions over time, you can extend this to that setting. We do that with Markov decision processes, and instead of doing regressions, we do something with the Bellman optimality equations. And so this can be applied in very general contexts. So maybe I'll just stop there. Thanks.
We have lots of time for questions.
I was wondering if, under the current election cycle, whether you've seen any of this type of methodology used to try and recruit people to vote or sign up for the early voting registration. You know, sort of like taking in data and collecting that information and knowing how to reallocate your resources to try and target people who are most favorable to potentially register.
Yeah, we did apply this to some old get out the vote data from, I don't know how long ago that was, maybe 15 years ago. So I've worked on it in a very irrelevant data context. But yeah, they're very interested in this. They're also interested in the spatial effect, because if I convince both of your neighbors to go and vote, then maybe you will be more likely to vote. So this thing we assumed didn't happen here, that your treatment doesn't affect my outcome. We want that to happen in the voting context, right? And so we do a lot of things where we do optimization of like social networks. So we haven't done elections, but we've done advertising. So if you're going to pay to place ads in a social network, where should you put them so they're most likely to spread and disseminate across the social network? So it's the inverse of the reverse of the disease problem, right? And I don't know that anyone has tried to do this, but it would certainly be, I mean, now would be the time, because you can get all this data and everyone is using social media, and so it's much easier to deliver these treatments sort of where and when you want. We have done things where we've identified focus groups. That's the treatment, is to pull you into a focus group when we're trying to understand people's views of rehab centers. So if you look at people who that have substance abuse and have been in contact with the rehab center, they talk about it very negatively. And if these people are very visible on social media, so we target those and say, well, come talk to us, tell us what you think we should change or how things can be different. So we've done things that are adjacent to that, I guess. But we haven't done it live now, and I don't know of anyone that's doing it, but yeah.
So I'm wondering, so with the advances in cancer care, how much of that can be attributed to advances in medicine, and how much can be attributed to smarter decision making? I mean,
Yeah, no, that's a great question. I don't know. I'm trying to think what the. So we're working on one of the iSpy trials, iSpy 2, and they're trying to do more adaptive kind of design things. And, so it's which is the bigger breakthrough? I don't know. I mean, identifying some of these biomarkers, which the tailored treatment has been, I think, a big thing. But also one of the big contributions in statistics and data-driven decision making has been uncertainty quantification. So is there really evidence that there's a difference between a new treatment and an old treatment in a particular subgroup? There's been a lot of work in subgroup identification that has received a lot of criticism because it wasn't done properly, and that has caused very real consequences. And so a lot of the work that goes along with this is, if I give you a regime, how much evidence is there really to recommend CDC over standard care for this particular subgroup or not? So I'd say that's another big piece. But I think in some of these examples, if you look at a tailored therapy versus a non-tailored therapy, there can be a big difference in terms of the average efficacy.
and then a follow-up question. How open are doctors to listening to this? Or are there old school, because I know we have such a hard time even getting them to ask one new question sometimes, and so saying, heavily rely on this data? I don't know.
Yeah, no, it depends totally on the area. So like cardiovascular disease was very, very slow to adapt this kind of thing. But like behavioral interventions, they got in this early, and we're very excited about this kind of tailored treatment. Some work in cancer did this. They didn't call it this, but like some of the early cancer trials where they would say they give everybody the first line treatment, and then they give you a salvage therapy that they randomize or a maintenance therapy that they randomize, and that was with some of the first the SMART trials. And so they were very interested in this, but then there's others that there are people who think that you shouldn't be tailoring treatment and data at all because there's not enough signal. So it totally depends on the owner. Yeah, and we get calls probably once a week to help people design SMART trials. And there are some people who want to do a SMART even though it's not appropriate at all because it's an exciting topic.
Buzz.
And then there are some that I think really have identified that you're giving treatment sequences and they really need to think about the entire package and not just one treatment at a time.
In that diagram where you had the 3 stages and you collect data, can you talk about like how long are each of these stages? How do you know you're done with one and before you move on? Yeah, this one.
Yeah.
How long do you collect it? How do you know that you're done?
I don't think you're ever done. I think it's the
Well, how do you know that you can move on to the next stage?
Oh yeah, so I can tell you about one where we kind of did this by design. So we have an HIV or an STI prevention trial. It's going to have about 4,000 people in it. And what we're going to do is we're going to enroll a small number as an internal pilot, go through this process, and then based on that adapt the next phase of the trial. So that's an example where this has been sort of self-contained. But otherwise, I think we had a fertility trial where they ran one 8 years ago. They got the data. They had some hypotheses. They went into the clinic and they sort of looked for anecdotal evidence. And now they're running a follow-up randomized trial. So that was 8 years, more than 8 years, because the trial ran before that. So it's like 12 years to go between this once and then this again. So I think it depends. Something like mobile health, you might be able to do this in a much finer time scale. You might be able to do this every day.
Yeah, that was sort of my thinking. I mean, if you look at the way machine learning is kind of moving, you're trying to think about adapting quicker and quicker. Could you even get like one data point and then start pushing a cycle? I mean, what would that look like? And of course, there's an ethics component right behind some of these things too.
Well, they're definitely doing that in mobile health. So you get an app on your phone, and let's say I'm a problem drinker, and what's happening is that it's going to warn me if I'm engaging in risky behavior. So maybe I'm somewhere where I've had a binge drinking event in the past, or maybe I'm with some people that I am prone to drink with, and so it could send me a message. It could say, is where you are more or less likely to make you to drink? That's the intervention. That's the whole thing, because it's just getting me to think about it, right? Or maybe that's not going to work for me, and it's going to say, we need you to call your sponsor right now, or we're just going to text them, right? That's a much more extreme thing. Or maybe it's going to send me a picture of my daughter who's going to say something to me about sticking with the intervention or whatever it is. And so they are adapting to the individual in real time, in an automated fashion. So that's sort of I would say, the setting that doesn't fall into this paradigm. This is more clinical trials. We're talking more chronic illness. But for the just-in-time adaptive interventions on the phone, we are adapting on a phone individually to each person in real time. So when you send me that message and I just turn my phone off, right, and the next day I report that I had a binge drinking event, that then updates the rule for me, right? And so it does update just on in shorter time with daily basis. We also have diabetes management, so type 1 diabetes problem where we're trying to help you adjust insulin. That's another one where we're doing it in real time, person by person. Yes, that's right.
Have you also tried to implement this into other kind of diseases like obesity, things that may not necessarily medicinal usage, but
Yep.
more so?
Yeah, so we have an obesity trial that looked at, this is kind of an interesting thing. They did something where you filled out a questionnaire about your diet, and then they asked you whether you'd like to go on a low carb or low fat. So okay, you could be randomized to them asking you. So I could say, do you want to go on a low fat or low carb diet, and you choose. Or I could randomize you to one of the two. We have your survey for all cases. Then the question was, would the people who chose do better because they felt like they were more in control of the diet, right? Or were the people who went against what their choice would have been better off because they would choose something that was closer to what they're already doing, and so the impact's going to be less? So either one has is kind of interesting, and so that was a smart trial type thing. And so we've done that, and then we've done an obesity trial within a type 1 diabetic population also. Yeah. Oh, there's another one. There's a mobile one. It's called Health Steps, Heart Steps. And I don't work on this one, but it was a mobile health intervention where they were trying to get people to take more steps throughout the day. Yeah, that's great. Yeah, that's an important application area.
So I had a question based on one of the last things you said about getting people to take more steps. I've read a lot about Fitbits and how they can be, like you're using bright data to increase movement and it can be really good. And but at the same time, people become reliant on these devices. So not like, do you see a negative like implication of, I don't want to say overestimation, but like, is there a risk of it becoming not like obsolete in its effectiveness, but producing some unforeseen negative outcomes?
Yeah, so I don't work that much with Fitbit data other than we have it in the diabetes study, but one thing that can happen is that people can optimize to whatever the metric is that you're using. So, and this is a common problem with reinforcement learning and sequential decision making. So whatever the criteria is, that's what they'll optimize. So maybe I will take more steps, but I'll eat worse, and I'll get less sleep, and I'll do other things that are bad for my health. And so overall the impact is negative. And an extreme example, when I was a graduate student, I worked on a trial where they came and said we're trying to minimize side effects. So they were giving these oral chemotherapy, and the idea was that the side effects would be less. So that was the outcome they wanted to use. But how do you get really good side effects? You don't take your pill, right?
Yeah.
So they were conflating. They had the wrong objective, right? So if I think I'm going to maximize side effect reduction, well, what's the answer? It's don't adhere, right? So you should give something that's really hard to adhere to. So that is one concern, is that they just sort of
Can you
adapt.
account for that in your, like?
We try to use it actually, because one of the things that, like so for the like binge drinking, you can have these long periods where there's nothing going on,
Yeah.
right? And so if you try to use the binge drinking events as your reward, or your outcome, not reward, but we call it reward in CS, but the outcome, they're so far apart from each other that you need a ton of data to estimate what the right strategy is. Just like if we were going to try to build a chess player, I could generate data where we go all the way to the end, and if I win, I get a point, and if I lose, I get a minus point, if we tie, I get a 0. And then I generate trillions of chess games to try to build a player, right? It takes forever to learn a player well that way. So what do people do instead? They use interim outcomes, right? So they use things like pawn structure and where your pieces are pointing. And in the addiction problem, we don't want to just use your engagement with the app. Are you talking to your sponsor? Are you opening the app every day? So engagement becomes the primary outcome because it helps you learn better to optimize the thing you actually care about. So actually you're trying to use this kind of, this difference in outcomes to your advantage, but you run the risk of optimizing the wrong thing. Maybe you get people who drink all the time but open the app a lot, right? So,
just related to this, does that provide a rationale for using not necessarily maximizing an average, but maximizing a minimum if you want to avoid the worst possible outcomes? And in which case you don't have something that really fits within a probability model, and so you have to change some of the approaches used?
So that's a great question. So there's a few different things. One, we can do things like minimizing the probability of an adverse event. Also, all of these statements are also conditional on the covariance. So it's not that they maximize a conditional mean. So that means after we adjust for all your x's, it's still optimal. So it would be optimal for people who are at high risk as long as the risk was captured with the x's. But there are methods for doing things like minimizing probability or doing a one-sided expectation where you only penalize if you're low but not if you're high, that kind of thing. Yeah. But it does become, you do need to, I think it's important to, once you estimate one of these, you do need to look at the population and see who's benefiting, because it could be that you're taking the people near the top and pushing them way up, and the people at the bottom aren't doing so well, so that's right, that's right.
You kind of touched upon this, but in regards to social media, I had learned in one of my health communication courses that they actually were able to pinpoint where the flu outbreaks were because of what people were posting on social media. Like, oh man, I'm feeling so sick, so they would actually send more vaccines to specific areas based on social media. Now, how do you foresee social media to continue to have an impact on really, healthcare, the entire industry? What do you think?
Yeah, no, I think there's huge potential in that. In identifying things like where the food poisoning outbreak originated, people are using data for that, things like outbreak of the flu or other diseases, trying to sort of pinpoint. It turns out it's really hard to do well. And there's this Google flu disaster, I don't know if you guys remember that, so they tried to do their flu forecasting, and if you compared that with the CDC's very simple model, CDC did much, much better. And that's because social media data is not representative of the population you're interested in necessarily. Sometimes it is. If you're advertising on social media, then fine. That is who who's going to see your ad. But if you're talking about making inference about everyone in, say, Florida, right, you can do some adjustment. So I think there's huge potential. What I see as being really helpful is balancing really cheap, high-volume data like social media data with very meticulously planned experiments to supplement, to calibrate that data. And so what we're seeing now is a resurgence of a very old idea from the census, which was double sampling. So you have your cheapo sample, and then you get your very strategic, expensive sample, and then you combine them in a way that gives you really good estimates for the least amount of resources. So.
We have a couple of studies going on right now with social media, and one of the issues we see is that we have very biased data, and we also have very poor quality data, and this one is very difficult to address.
Yeah.
So.
And it could be that you just have to run a separate, smaller experiment to just do some recalibration. Yeah.
Something I think about is like what I see, like maybe even some of my older family members, some of my classmates post, oh, I definitely have the flu, I'm definitely sick, I definitely have this. Like, do they really? Is what people posting on social media really an accurate portrayal of what is actually going on with them? So I can imagine that's probably difficult, but like a merging of the two.
Well, and if you're really, really sick, you're not posting on social media, right?
Exactly,
So
right?
that's
Yeah.
another thing that happens.
How do you explain this to patients? So, it's one thing to explain decision lists, I think, to clinicians and other people who have training in the area, but if we think about wanting to empower patients to participate in their decision making, how do we explain to them the data that backs up their recommendation or open up the potential for input or choice based on factors that might not be related to the medicine, like?
Yeah, so that's a huge open problem, and I don't have a good answer. I think we're trying to build a hybrid decision systems where you have computers and experts working together, but those are experts, not the not the person who's actually consuming the healthcare product, right? So people have worked on that. People do these things where they try to show like, here's 100 people, and it's just a little. You guys have all seen these. I think 100 stick people, and they show 3 of them are red that they had a bad outcome, and 53 of them are blue, they had a great outcome, and the rest of them are green, they had like a mediocre outcome. I don't know. We do communicate decision rules to stakeholders in these ecological decision problems. Those are the ones actually making decisions, but they are used to trying to assimilate various data streams and make decisions. And so they're much more nuanced, and even there it's very difficult, at least that's what we find. So I'd love to get your input on that, because this is our attempt to be more interpretable for the middleman in the process.
In the simulations you ran, you had a 100 data set and a 400 data set. Did you just arbitrarily pick those numbers, or where's the sweet spot?
Oh, so we chose 100 because the data example, which I didn't show you, had 100 patients, or 111. So we just tried to say, this was our motivating application, so we wanted to match that. But then that's actually pretty small. It's on the smaller side of the kind of trials uses data, so we picked 400 as just a more realistic. We usually use 500 to 1,000. So more or less arbitrary, although the 100 was justified, and we just sort of scaled it up. But uncertainty quantification would tell you about sort of whether or not you have enough. that's something we're still working on in terms of the inference.
So we're seeing fewer and fewer of the really large-scale randomized controlled trials being done, definitive treatment A versus definitive treatment B. It's much more subsets, much more biomarker-driven precision medicine studies, where maybe there's 100 patients, but there's only 3 with a certain genotype.
Yeah.
And there's that setting is replicated 30 times, and that's
Yeah.
your 100 total patients. So I worry a little bit that we're getting a lot of in-depth data, so a lot of covariables, but
Mhm.
very limited number of unique individuals that are assigned to each of those covariates.
Yeah, I do have a bunch of data sets like that from I also work at spinal cord injury in dogs. So we get trials with 14 patients, and it becomes a lot more exploratory in trying to visualize the results and identifying. I mean, you can sometimes get a significant result, but it also becomes more about extracting meaningful pieces from the data to then confirm if you're talking about subgroup identification. So we might say it looks like dogs, patients with this are the ones that are responding to this drug. And the spinal cord injury, they get this big difference. Some dogs start walking, doing fine, other ones have no response at all. And they're very interested in figuring out why that is. And then they run a follow-up study. So it could be that you just can't get good error rate control, but you can generate hypotheses that you then just have to run another trial. But these smaller trials, you have enough power to test. You probably do not have enough power to identify a subgroup, but you have enough power to test a subgroup you specify ahead of time. So that's the reason for having multiple trials. Identify the group and then evaluate it in a totally independent patient population.
All right, well, I think we're out of time. Thanks again to everyone for coming, and thanks again to Eric for